Good evening and welcome to EE 5141 Introduction to Wireless and Cellular Communications. I'm Professor David Koilpillai and very happy to have this opportunity to teach this course for this batch. I thought I would start off by just saying a few words about the course, but even before that, maybe answer a question that's on your minds: why in the studio? One of the feedback points that we have received, at least I have received over many years, is that students find it very hard to write what's on the board and also listen at the same time, because information is coming at a very fast pace. So the suggestion was, at least can we have the notes after the lecture is over? And unfortunately, many times what's written on the board is very different from what I have in the sheet of paper, because some things are changed as we progress. So I thought the best way would be is to find a tool or a way by which we can capture whatever is happening in the classroom, whatever is on the board, as at the same time have the flexibility to introduce a PowerPoint or a MATLAB simulation or an animation. Those things we could not do in a traditional classroom. I'm sure you know that in many of the ESB classrooms we have projectors, but they're off into one corner. It's not easy to switch back and forth. So this is a way, hopefully, by which we can use all the information in the different forms. And also at the end of the lecture, you will have something that you can go back and refer and also look at in terms of the information. So as the screen is coming up, I just wanted to mention a couple of points regarding the timing. This is an F-slot course, but it's a 4-credit course. So in addition to the morning slots, we have one afternoon slot, which is the Tuesdays at 4:50 to 5:40, and we'll keep the slot as at the present time. Let's see if we can shift it to an earlier slot in case this is there is an earlier time slot that is available to us. So one of the ways that I like to keep track of what is planned for the lecture is to have a quadrant where indicate what is going to be covered in the class. So we've already addressed the first 2 points, Y Studio. Hopefully you'll at the end of the course you'll be able to affirm that this was a experiment worth doing. Let me start with the course flyer. Maybe before that, my room is in ESB 339A. You're welcome anytime to stop by if you have something to discuss. Let me look at the course information. And let's just sort of highlight what we would be covering in the course, because it's always good to know where we pick up and what we plan to cover in the course. The first week, that is this week, we are going to give an overview of the cellular systems and introduction to wireless communications. So you may know, well, this is familiar stuff, but just wait until the information is shared, because there is a lot of activity happening in the arena of cellular, and it's good for us to get a comprehensive view. The wireless course is going to focus on one specific aspect, and but it's good for you to be very comfortable with the terminology, with what's happening in 3G, 4G, 5G, whatever may be the question. Many of the things that we are going to be talking about pertains to the wireless channel, very specifically to the wireless channel. So one of the first things that I would like the students to be familiar with is to have a baseline digital communications link, whichever you would have done in your digital communications course. We will then change the channel according to what the type that we are studying. So we will talk a little bit more about that in the course. So one of the things that we do in first week is for everybody to have a baseline MATLAB or a C simulations that will be part of an assignment. We then move into understanding cellular, the way it is deployed today. How did where did the word cellular come from, and what are some of the salient features? Probably the most important is the design of cells, how the cells are deployed, what happens when you move from one cell to the other. That's the aspect of handoff, and then the notions of capacity. What's the capacity of a cellular system? Now, having understood cellular, then we go into the heart of the course, which says that how do I understand the wireless channel? We call that as propagation and understanding the effects of propagation in the context of what we call as small scale effects. And we will talk about it in today's presentation. What are some of the distinctive features? What makes it different from an AWGN channel, which you probably would have studied. So here are some aspects that we will cover in a fair amount of detail, and the computer simulations will now move from a basic digital communications link to a wireless channel with the impairments of a wireless channel. So that's the second step. One of the things that we will find in the context of the wireless system is that having multiple antennas is a significant advantage. One, it tells us that we can have the feature called diversity. It also helps us in terms of the capacity, how we can improve the capacity of a system. So diversity and capacity sort of go hand in hand. And along with the diversity, what happens if both transmitter and receiver have multiple antennas? Those are called the MIMO systems. So the fading channel, understanding it in full detail, understanding what are the benefits of having multiple antennas at the receiver, what is the capacity of a system, what happens if you have multiple antennas at the transmitter and receiver, that would be the MIMO system. And then we move into what are the cellular systems that you are looking at today, the basic concepts of CDMA, which is the third generation system, OFDM, which is the fourth and fifth generation systems, and that is pretty much the span of the course. But one very important element that is that you should know as a student who has studied wireless communications is what happens when I set up a tower at one location and then try to receive it inside of a building. Basically, what happens due to walls, what happens due to buildings, that's what we call as the large scale propagation. And again, those are well understood, well studied. We will touch upon that, making sure that, if somebody were to ask you to design a wireless system, you will know exactly how much power to use and what height of antenna to use, and all of that will be well understood. Okay, so that is more or less the course. When you get a chance, you can go through in detail. If you have any questions, feel free to let me know. There's not a single book that would be complete for the entire course. So what we are going to be using is a combination of books. Rappaport has got a bulk of the information, but Goldsmith, Say and Vishwanath and Molish have quite a bit. Some parts on the CDMA side will be taken from Haken. Of course, many times we'll have to go back and refer to Proikis, because a lot of what we talk about is digital communications applied to a wireless channel. The course plan is given in the flyer. You can take a look at it. Sort of tells you approximately how much time we will spend. The total course is 56 lectures. Have a buffer of 4 in case we need to spend a little extra time on any of the units. So that is a quick run through of what the course outline is going to be. I thought I'd also take a few minutes to share about the philosophy of the course. Most students taking this course, I assume, have done digital communications either at IIT or at another institution. So what we are going to be doing here is actually building on the digital communications foundation that you have. So what you will find is the way we cover the material, a lot of times will be a quick review, applying it to the wireless channel, expand the wireless portion of it and our understanding of it, and then develop the entire framework around that. So whatever you have done in digital communications, so for example, you've studied information theory, how to represent signals, how to compress signals, how to do channel coding, modulation, all of that we assume is understood, and we just sort of take it from there and then say, okay, how do we apply it in the context of wireless? What are those things that are advantageous? What are those things that are difficult? So typically in a digital communications course, you would have looked at an impairment of AWGN. Apart from that, I'm sure you would have studied channels which have intersymbol interference. So what we are going to be looking at is take those two impairments and add to it the aspects of a wireless channel, which we will refer to in terms of fading, multipath, Doppler. Those are all elements that we will introduce. So As I said, the approach is going to be pick up what's there in digital communications, assume that the students are comfortable with it, wherever necessary, do a quick review, and then focus on the wireless side. On the receiver side, again, in digital communications, we typically study how to build receivers, talk about synchronization, how to do timing, how to do the demodulation, decoding, all of that, again, we assume is well understood. We will build from there. So our progression will be from the digital communications part into the wireless communications and make sure that we are comfortable with all aspects of that. So let me maybe share a few general thoughts on what I would consider as outcomes for our course. The outcomes that would be very good from a teacher's point of view would be that this course would give you an exposure. So let me capture that. Outcomes would be an exposure to what is happening in the world of wireless, the current cellular systems. Second element would be the analytical understanding of the wireless channel, our understanding of that. So it would be the physical, the mathematical or the analytical aspects of that, and also along with that, intuition. Very, very important, because a lot of wireless is about being intuitive, understanding what is it that works well in the context of a wireless system. Then the simulation aspects, I think that is a very key element that I would like to capture in our course. And also talk about the problem solving aspects. We will do assignments on the different topics that we are studying, and finally, hopefully, whatever we do in this is a preparation for further study. For further study, or whether you're doing a project or research, or you're going to be a practitioner. I think all of them are equally, we will prepare you for that. Another element is it's a traditional course in the sense that the evaluation will be very much along the traditional aspects. We will have 2 quizzes, quiz 1, quiz 2, end semester exam. 20% for quiz 1, 20% for quiz 2, 45% for quiz for the end semester exam. Assignments, our course is very much assignment based. So assignments will carry a fair amount of weightage. 15% will give you a little bit more information about the assignments themselves and how we will carry it out. A lot of it will be using for computer simulations, it will be online submission. For written assignments, it will be evaluation will be done in the form of a assignment test that is done in the class. So this is sort of a very traditional course in that sense. But I thought I would like to share with you a little bit about a strategy. As a student, always wanted to know what the teacher thought was a good strategy for the course. So maybe I should share that with you. Please stay abreast of the class, because this is a course that actually does cover a lot of material, covers it at a fast pace. So please stay abreast, reading up on the corresponding chapters in the books that we are currently following. But of course, having 5 books is an advantage, because you can always cross-refer and get a very rich understanding of the wireless, because each of the 5 books that we've talked about have been written with a very specific perspective. So when you look at the outcomes, you can almost map, this book will give you a good exposure, this will give you analytical tools, this will give you simulation. So I think you can almost understand, so keeping it in perspective. Let me share with you a presentation which I have prepared very specially for the course, and so that we can have an opportunity to dialogue a little bit. So this is a way by which in a nutshell, very, very briefly, you can get a bird's eye view of the entire wireless domain, and then we will zoom in and look at specific aspects of the topics that we are interested in. They say that it's always good when you want to look ahead, always also good to look back. So let me take you on a few minutes journey to back in time. A lot of times when the question of who invented wireless comes about, the answer seems to be it is Marconi. But if you go and look at IEEE's history site, the credit has now been officially changed from Marconi to J.C. Bose because the experiment of Marconi was in 1897. Several years before the transatlantic experiment, but just the wireless demonstration. But almost 2 years prior, J.C. Bose had already demonstrated wireless in the city of Kolkata. And in fact, apparently J.C. Bose and Marconi met in UK, but by that time J.C. Bose was on to other things. He didn't pursue wireless, but Marconi did, and the rest of it was history. But the first demonstration, the credit goes to Marconi. Today, cellular is a common man's technology. So if you were to ask for images that describe cellular, probably you think of towers in your neighborhood, or you think of the SIM cards, or the Google Maps, or just people looking for information, and a whole variety of handsets. Today it has become very much a common man's technology. But when did it actually start? And just a historical perspective, 1895 was J.C. Bose's first experiment. Transatlantic experiment transmission by Marconi was 1902. The first users of wireless communication were police and the armed forces during the World War, both the World Wars, but by and large the commercial use of cellular did not start until much later. The first analog systems, what we refer to as the precursor to cellular as we know it today, what would be called as the 1G system, that came into existence in 1981, not very long ago, in the context of the development of technology, because wireless actually had happened in almost at the turn of the century. The original credit for inventing or the concept of cellular goes to Bell Laboratories, the famous laboratories of the AT&T company. The first time digital cellular was introduced was 1991. And after that we saw the evolution of digital cellular. The CDMA systems came in. 2002 is 3G. Now you may say, well, I thought 3G was not deployed until a few years ago in India. This is global perspective. India happens to be one element of it. We will look at India perspective, but this is what happened globally. And while we had not yet even deployed 3G, the world already went on to introduce 4G, and now we have India's deploying 4G very aggressively. We are also participating in the 5G discussions. The last line tells you how steep the market of cellular systems have grown. Anyone who's interested in business always likes to ask, what's the size of the market, because that tells you what's your potential for revenues and how attractive the market is. Even way back in 2011, the total global market for cellular had already crossed 6 billion. So it's a huge market by any measure. One very reliable source of information for Indian scenario is from the Telecom Regulatory Authority of India, TRAI. They publish a quarterly report. We will upload the latest quarterly report in the Moodle website, but I have to look at the size because these documents are slightly large in terms of size, but you can download it. It has very, very good information. I've extracted the most important and relevant information, hopefully just so that we will get a good feel for what is happening. Okay. Now the growth of cellular in India. You may see, well, it doesn't look like India is growing very fast, but look at the numbers. We had crossed 930 million, and that was in 2014. May 2015, India crossed 1 billion subscriptions. And what is interesting is the fact that the amount of wireless that is present in the country, the entire blue segment and the burgundy segment together represent wireless, and the small slice is the wireline, and it is actually decreasing. Our wireline deployments are actually going down while the cellular is going up. Another very interesting data which is good to keep in mind is that today when we talk about broadband and how people are accessing broadband in India, 93% of users are accessing broadband over wireless devices. So again, here is a very interesting or a very compelling story why we as Indians should be very interested in wireless. Not only is it a big market globally, that more or less defines how we use the technology, as well as how broadband will be used in the future. So interesting perspective. Now, just to get a feel for where cellular fits in the big picture of wireless. Wireless is not equal to cellular. Wireless is much bigger than cellular, but cellular happens to be the dominant technology that is there. So if you look at the range or a hierarchy of wireless systems, starting all the way from Bluetooth, I'm sure everyone is familiar with Bluetooth and Zigbee. Those are what you would refer to as personal area networks. Typically that would go in the range of 10 meters, of the order of 10 meters. The next in the hierarchy is local area networks. Of course, all are wireless technology. So it's wireless personal area networks, wireless local area networks, technologies such as Wi-Fi. So that's the next hierarchy in terms of the distance. Then where does cellular come in? Cellular says, okay, it is much more than a personal area or a local area. It is something that can cover large geographical areas, wide area network. That is our cellular technology hierarchy. Now, there is one which is bigger than cellular, that's the regional area networks. Typically, those are what you would refer to in the context of satellite. They cover continental coverage. That is not our main focus. And there are also some which are smaller than a city-wide deployment called metropolitan area networks. So a little bit less limited in terms of their scope, not as wide as cellular. Those are called metropolitan areas. So the three technologies that would be very important or interesting for us: personal area, local area, wide area, and cellular is in that range. One very interesting fact about cellular in India is that the base stations are, the infrastructure with which you connect. We started off putting them 4 to 5 kilometers apart. Then they moved to 3 kilometers, 2 kilometers, 1 kilometer. Now, inter-base station distance in urban areas is less than 500 meters. So every 500 meters, on average, you expect to see some sort of cellular infrastructure. And the driver for this has been the capacity. The only way we can increase capacity is by increasing the number of towers or cell sites, and we will talk about that in a little bit more. But it comes at a price. And the price invariably is the amount of interference you are generating. So from a design perspective, capacity is good, interference is bad, but there's unfortunately the only way we have to find a good balance between that. Another interesting thing that you want to at least make a note of is that cellular is a licensed technology. You cannot transmit in the cellular bands without a official license, whereas the technologies such as Bluetooth and wireless LAN, those are unlicensed technologies. So again, there is a difference between the two, something to just keep in mind. We are talking about licensed technologies for which an operator has to bid for and pay license fee before they begin operating. Many of you, probably the first phone you owned was a smartphone. So may not have seen what the phones were that preceded this. We'll spend just a couple of minutes just to tell you a little bit about what phones look like, and so that you can. The phone on the left, 1920, is a rotary phone. and that actually lived for more than 60 years. Even up to 1980, we had rotary phones. So that was a landline phone. The first sort of wireless phones were the ones that were used by the military. You can see old military phone up there. They had to wind it up to generate enough charge so that they could communicate, but it was a very rugged one. Very interesting. Motorola was the first company that made these devices, and it used to be a company called Victrola. But because they made the devices that were mobile, they said, okay, it's no longer Victrola, we make it Motorola, because they are moving devices. So again, they have been a pioneer, and over the years, they have been the ones, one of the companies that have pushed the envelope of technology. So the first handheld phone was almost a foot in height. 1973 again came from Motorola. As you can see, was being held here. But of course, this was a very power-hungry device. May last only a few minutes, less than an hour in terms of the battery life. So you really needed to keep charging it. And this was the entry point. So people actually wondered whether this will ever become a commercial technology, where it will become a mass market. And there were predictions saying, no, really, that is not. It's not going to be a mass market. Nobody is going to be carrying around a big device like this. What it is going to be, it's going to be a status symbol. It's going to be an elite symbol where the very rich will have phones like this in their cars. That was the projection, that if you had a phone in your car, then you belong to a certain social status. Never looked at that it would be a common man's technology. So this was what it looked like, the battery pack. Huge battery pack and the device, and this would be installed. The battery pack would be in the trunk of the car, and then you would have the phone near the driver's seat. So that was how it started. So occasionally, if you didn't want your phone to be stolen, I guess you had to carry the battery pack with you, or if you wanted to communicate for an extended period of time. But fortunately, the sizes became smaller, and the phones became had to start lasting a little bit longer in terms of battery life. The first sort of palm-sized phone. Palm-sized came from Motorola, 1989. This was a device that was so small that when you held it to the ear, the microphone didn't reach your mouth because it was so small. So Motorola came up with a very clever technology. They called it the flip technology. The flip opened out, and then the microphone was located here. So that's the only way they could make the distance between the ear and the mouthpiece. So again, very interesting piece of history, and this also served a very good purpose, because once you closed it, you couldn't accidentally press the keys. It sort of became a inbuilt keypad lock protection. Okay. Then came a series of what by the way, this one had a one-line display. Just only digits it could display. The big jump came when they could get a three-line display, dot matrix display, a few characters. You could see the number of bars to get the cell strength and your battery life. But that was the displays that we had in 1992. Then Motorola came up with another variation called StarTAC, in which case now previously the mouthpiece was opening out. In this case, the earpiece was opening out. Again, very interesting designs. But probably the most widely sold phone in the early generations was a Nokia phone, 1998 to 2000. They came up with this phone. And then this was around the time that people started saying, cell phones cause cancer, right? It became a big concern, because it was starting to enter mass market, and Nokia did a brilliant strategy. They put the antenna inside. It was a built-in antenna. And I've heard some salespeople say, well, that doesn't have an antenna, so don't worry about cancer, everything is okay. It was very much there, but the antenna outside is actually a better design, because it gives you better link margin. We will talk about it. But today it is by design put inside the phone, so that it sort of adds to the aesthetics to not have something sticking out. Okay, The first QWERTY keypad came out in 2002, and of course the minute the iPhone came around, the whole smartphone phenomenon started 2007. And so this is on the right hand side, you see the Ericsson family started out with a big phone, went all the way small, and I guess now we are back into somewhere in the medium size. So that's been a very interesting evolution, what happened in terms of the cellular handsets. But we are a technology course, again the cell phones are one aspect, but what was the functionality that each of these devices gave? First generation was all about voice. Voice was carried as an analog waveform, basically FM type of transmission, and therefore the focus was on providing voice. The minute digital came along, the voice was no longer a waveform coding, it was a vocoder, basically representation of speech using a speech coder, which means that now you are doing digital representation of voice. So that's what we refer to as digital voice, or in other words, digitally compressed voice. And circuit switch data at 9.6 kilobits per second. There was a discussion, should we have SMS or not, because nobody could figure out what SMSs would be used for. So eventually they decided, okay, let's keep it in there because somebody someday may find a way to use that. So that's how SMS came in, but of course today it's a different story. SMS is a key driver. Circuit switch voice was replaced with packet switch voice in the 2.5G area. Many of you are familiar with GPRS, General Packet Radio Service. That was the first time packet switch data was introduced. The data rates, we were looking at 9.6 kilobits per second for circuit switched, increased a little bit to 14.4, but packet switch you could use, could support higher data rates. Third generation, there was always an understanding that the growth is now going to be in packet switched, so the data rates for packet switched went from 384 to 2 megabits per second. The entire range was there. Voice was significantly improved, and then we started to see more and more data applications, all of them using the packet switched data. 3.5G took the speeds up to 14 megabits per second. 4G has taken it even higher. Now in 5G we're talking about 100 megabits per second. So now the question that is often asked is, well, what application do you have that runs at 100 megabits per second, or that requires 100 megabits per second? The answer is very simple. Remember, wireless is a shared device, shared medium. So 100 megabits per second over the air does not mean that your device alone is getting the 100 megabits per second. There are several people who are contending for the 100 megabits per second. So what eventually gets down to you depends on the number of users, and therefore the individual data rates are still modest. It's not a dedicated rate, and that's why the push has always been, let's see if we can push the data rates a little bit higher. A very good way for you to sort of keep the cellular evolution in mind. Again, maybe it's a good idea to, when you get a chance, create a acronyms sheet, which, all these different acronyms, I'll just mention them. The second generation was GSM, Global System for Mobile Communications, GPRS, General Packet Radio Service. That moved into a technology called wideband CDMA. That was the third generation. Then we started to see the 3.5 generation, and then the fourth generation was a system called LTE. Again, the names may not be very logical. It's called long-term evolution, and a very interesting phenomenon to observe. GSM and CDMA were actually competing technologies. Some of you may know that the operators also were competitors. Each of them was evolving on a path of their own. But when it came to the fourth generation, they merged into a single system, which is long-term evolution. So long-term evolution went to 4.5G, which is called long-term evolution advanced, or LTE advanced. And then we're now talking about 5G, which will be in the future. The year is predicted as 2020. As the target dates. So the main aspects that we have been looking at in the evolution, as you saw, was the increase in the number of increase in the packet data speeds. As you were increasing the packet data speeds, the number of users around the world increased several fold, basically growing exponentially. So how do you support increasing number of users, each user asking for more and more data rate, and your spectrum available is still very limited? So the challenge has always been, how do you support more users, higher data rates within the given bandwidth? That is what we refer to as spectral efficiency. Okay? And we will study, this is going to be a very key element of our course as well. A couple of conceptual pictures to keep in mind what is the trend of cellular versus other technologies. So if you remember, we talked about personal area networks. Personal area networks like Zigbee and Bluetooth, how do you characterize them with respect to cellular? One way to characterize is on a chart which shows the data rate on the x-axis, data rate in megabits per second. If you can see the x-axis, it's data rate in megabits per second. On the y-axis, it is coverage or mobility. How much can a user move and still be connected to the same system? So Zigbee and Bluetooth are fundamentally systems that do not provide handoffs or mobility. So more or less you are within a room or within a building, but the data rates can go, in the case of Bluetooth, up to 1 megabit per second, and a little bit higher in the newer evolutions of Bluetooth. Now compared to that, GSM or CDMA would give you coverage across a nation. Basically you can have nationwide footprint. So you could have full mobility, low speed all the way to high speed on a fast moving car or train. So you could have mobility and global national coverage, but the data rates would be very modest. 9.6 kilobits per second would be the data rate. So you can see that it would be very strong on the Y dimension, not so strong on the X dimension. So the cellular technologies basically said we need to fix this as the system evolves, because people are going to ask for higher and higher data rates, but we don't want to lose the advantage that we have in the cellular system, that you have mobility and wide area coverage. So 2G to 3G to 4G, you can see basically the curve is shifting to the right without compromising on mobility or coverage, but all the while increasing in terms of data rate. On the other hand, wireless LAN technologies 802.11 will always seem to be one step ahead of cellular. By the time cellular came to 1 megabit per second, they were at 50 megabits per second. So basically the wireless LAN technologies are stronger on the y-axis, but again limited in terms of their mobility or overall coverage. It will still be inside of buildings. So an interesting dynamics between how cellular systems are evolving, how the the wireless personal area networks and local area networks technologies are evolving. Okay, good to anchor whatever we say in the context of what we already know. So I think it is good for us to now say, okay, what are the components of a digital communication system? So this is a review. So hopefully all these pieces I'm going to refer to are things that you have already studied in one of the earlier courses. So if I were to ask you to draw the block diagram of a transmitter, I'm sure you would get most of it, but let me just sort of walk you through the flow. You have an information source to which you would apply source coding or compression. Basically, if it could be an analog source like speech, you digitize it, you compress it. That's your first step. Second step would be privacy, encrypt the information. Then you're going to send it over a channel. You want to do error protection. We are doing carrier modulation, so therefore you have to put the information onto a carrier. That would be the modulation aspect. Why pulse shaping? What is pulse shaping? Okay, pulse shaping you're using to introduce ISI? Well, I could use a rectangular pulse, so I don't do any pulse shaping, that would still be, okay, just make it bandwidth efficient. So the pulse shaping is our transmit filtering to make sure that our transmitted spectrum is as compact as possible. So depending on how you implement your transmitter, even the pulse shaping is probably done in a DSP. Then after that you convert it into an analog waveform, then you convert it into RF, do the power amplification, and then you connect it to an antenna for radiation. So this would be the digital communications block diagram. So some representative numbers. If you are talking about speech sampled at 8 kilosamples per second, 8 bits per sample, you would have 64 kilobits per second. That would be the transmission rate or your information rate. The first step of doing the compression in the case of GSM reduces it from 64 kilobits per second to 12 kilobits per second, and that is the voice coder or the vocoder that we use to transmit information. Error protection, very sophisticated error protection codes are available. Some error protection codes, most recent ones, turbo codes, LDPC codes, yeah, several of them, but the earliest one that we know of, or the easiest one to understand, is repetition codes, never used but used for illustrative purposes. Basically you repeat information or protect your information so that at the receiver you can always recover the original information. Modulation, several forms of modulation. Most of the techniques that are used in wireless are modulation techniques that use both amplitude and phase. I've shown you an 8 PSK constellation, 16 QAM is another constellation, but you will find that a lot of wireless systems actually work with QPSK, and by the end of the course I hope you will give me an answer why not 64 QAM or 256 QAM. Okay, now the block diagram on the receiver. By the way, notice the flow of the arrows going from the information source all the way to the antenna. Receiver is basically going in the backward direction. You take the signal, you filter out, that's your receive filter, throw out all the unwanted information, take only the signal of interest, amplify it. We call it a low noise amplifier. Again, a good question is why should it be low noise, but I'm sure you know the answer to that. Convert it back from RF to baseband, either in one step or in multiple steps, heterodyne or homodyne receivers. Convert it into digital, pass it through a matched filter. So if you used a square root raised cosine at the transmitter, a matched filter will give you the best SNR, and then you would do the demodulation, extract the information, remove the channel coding, get only the information that you are interested in, undo the encryption, and then do the re-encode the information so that you can then play it back. So some of the techniques that a receiver would need to do is synchronization, both frequency and time synchronization. If you are a coherent receiver, you would have to do channel estimation. If you have ISI in your channel, you would have to do equalization, and then of course you have channel decoding, but at the end of the day you probably don't care what is happening inside. You're interested in either the MP3 player or the camera, because the application is probably what is more interesting from an end user perspective. But from a communications engineer perspective, well, our focus is on the transmitter and receiver. So now, where is our course? All this is already studied. Where is our course? So here it is, the full transmit chain. Pick it up at the transmitter, already radiated signal. At the other end, the receiver, it picks up the radiated information, the receiver. So let's say it was an audio source, you spoke into the microphone, here the speaker is playing. What is sitting in between is the wireless channel. That is the focus of this course. And you might say, well, you know, what can be so difficult? You know, at the end of the day, I transmit, I receive, what are some of the challenges there? But that's the crux of this of the course, and that's what I would like to share with you in the next few slides. What makes the wireless channel so different? What makes it so difficult to work with? Why is it that we have to spend a whole course studying about the wireless channel alone and still maybe not able to cover a lot of the things that we need to look at? So interesting, our focus is going to be more or less around the wireless channel. Use everything that you have studied in digital communications, but apply it in the context of wireless, adapt it to the context of wireless. Okay, wireless channel. So in the next few slides, I hope to convince you that the wireless channel is sufficiently different and sufficiently challenging as well. So let's see if we can take a look at that. So the first and foremost element that I want you to keep in mind is that the frequency range of transmission that we are talking about, wireless transmission, particularly in cellular system, is between 1 and 2 gigahertz. 1 and 2 gigahertz. So in that frequency range, many objects which are very smooth, like the surfaces of buildings, can act as reflectors of the signal. Okay? So which means that if I transmit a RF signal at 1 gigahertz or 1.5 gigahertz, what ends up at the receiver is not a single copy of the signal, but it could be an unknown number of reflected signals. Now this is what we refer to as multipath propagation. Multipath propagation is one of the fundamental differences between other types of channels and the channels that we are talking about. Okay. Now as you know that the phase of the received signal, of the electromagnetic signal, can be represented in terms of an amplitude and an angle. Basically it's a phasor representation. So each of these copies of the signal is coming with a different phasor weighting factor. Okay? When I add randomly phasors, they may add constructively or they may add destructively. So I have no control over when these phasors are random. So when you study these sort of dense scattering environments, this is what we observe, that the signal is not always constant. At one point it is a signal with good amplitude. I move by lambda by 2, half a wavelength, and then the signal becomes, all of a sudden the signal amplitude becomes very poor. Then again I move by lambda by 2 in any direction, it becomes higher. Now lambda by 2 is not much, because take 1 gigahertz, 900 gigahertz easy to 900 megahertz is easy to calculate. Wavelength of 900 megahertz, C by F, right? So it's 1/3 of a meter. Okay, 1/3 of a meter is approximately 30 centimeters, 35 centimeters, half of that is 15 centimeters. So you don't have to move much for the signal to change. Now most people probably knew this without having to go through this explanation. If you don't get good signal on your phone, what do? You move your head. What did you do? You moved by lambda by 2 and you got a better channel. So that is as simple as how the channel changes. Okay, so now I don't know, this point where I am sitting may be extremely good, but where the first row is, it could be a very poor signal. Now this is what we have to deal with, that there is a spatio-temporal pattern which is not known to the receiver. My receiver does not know it's in a good channel, his receiver does not know it's in a bad channel. Basically it has to adapt. Now this is a very, very important element, because if you happen to be in a location where the signal is bad, you must move in order to get a better signal, otherwise you will not be able to communicate. So there is a issue of a loss of signal if you don't do something to remedy it. So there is a challenge that we have to work with. Now there is no guarantee that all the copies of the signal came at the same time. They could come with delays in between them. So then what happens, if you have copies of the signal which are delayed in time, that is called intersymbol interference. You get intersymbol. But now notice it's not fixed intersymbol interference, it is time varying intersymbol interference, because the first path could become strong or weak, the second path could become strong or weak, the gap between them could change, because if the car was moving, you don't get reflection from this building, but now you get the reflection from another building. So it's time varying intersymbol interference, which is very, very difficult, because this is something that we have to work with. So as you know, when I have intersymbol interference, I have to design an equalizer. If it's a spread spectrum signal, I use a technique called a rake receiver, but the rule of thumb is computation complexity is going to increase. Added to that, it's a channel which is constantly changing, so therefore be ready for a very complex receiver. This is one aspect of it. Now the second element of it is when I start moving. Now here is the element where multipath and Doppler start to interact. Now notice that this is the spatio-temporal pattern. Now I am a user who is starting at this location. I am going to walk across the room. So which means lambda by 2, every time I cross lambda by 2, my signal is going to go up, down, up, down, up, down. So to give you just a flavor for how much the signal can fluctuate, take a handset that is in a car that is moving at 60 kilometers per hour. In the duration of, it should be 200 milliseconds. In the duration of 200 milliseconds, this is the amount of fluctuations that you can see. Several of them which have fluctuations of at least 25 dB or more. So just so that, keep that number in mind, we'll come back to addressing why this is a problem. So if you are a user going across at 60 kilometers per hour, your receiver is seeing up, down, so very, very rapid fluctuations. It could be having ISI, and you have to build. So you have to have a receiver, first of all, that must adapt to signal fluctuation. It must adapt to ISI that is constantly changing, and this very fast changing of the channel. So basically the wireless channel is a channel that is very hostile. It is very complex to build a receiver, and it is computationally complex, but what the user wants is a handset which will last for 2 days, 3 days. So which means that you should not be drawing a whole lot of power. You cannot use a lot of signal processing or computational power on the handset. So how do you build a low power, low complexity receiver that will work in this type of an environment? So that's the starting point of our understanding that there are significant challenges for us in the context of the wireless channel. Let me just indicate what are some of the other impairments that we have to do, and then I'll open up the floor for some questions. So the idea of cellular systems is that we have many transmitters. So you can think of these hexagons, and in the center of each hexagon as a transmitter being located. So of course I cannot have two adjacent sectors transmitting at the same frequencies, two adjacent hexagons. So what I do is let's say I use a frequency A1 in this location. I move some geographical distance away from it and then reuse A1. So basically the only thing I am relying on is spatial separation to prevent these two signals from interfering with each other. So this type of interference is called co-channel interference. Two users who are using the same frequency but are separated by geographical distance, that is called co-channel interference, that is coming from different cells. Now in CDMA systems, spread spectrum systems, I am sure you would have studied that all the users in the particular location use the same frequency, and they have different signature sequences to separate them. So which means that co-channel interference for a CDMA system is very, very high potentially, because everybody in the cell is also using the same frequency. At least in the case of GSM, you had geographical separation. Here there is no separation, you are basically in the same cell. So there are two types of interference. One is intercell, that is coming from another cell but using the same frequency. The other one is intracell, those people who are in your own cell who are causing interference to you. Bottom line, all cellular systems are interference limited. Ultimately, when your call drops, it is because the interference level went up to a certain beyond an acceptable point. So the key point that we need to understand in the context of cellular is how do you mitigate interference. Whatever the multiple access method you want to use, TDMA, CDMA, whatever it is, at the end of the day, it's going to come down to the question, how do you mitigate interference? That is going to be a very, very important element. So what we now want to do is, you know what a link budget is. How much transmit power should I use to receive a signal at a certain level? I would now, in the next class, we will start by asking the question, how is a wireless link budget different from just a link budget that you would have done for a AWGN link or for a digital communications link? What would be the aspects that are different, and how is it going to impact the design of the systems that we will take up from that point? Okay, so this is sort of a entry point into the discussion on what cellular systems are doing, what is a wireless channel, why is it different, and we start getting into the details starting in the next lecture. Let me take a few minutes to answer any questions. Any questions on what we had covered so far?
Sir, recently I heard that Bluetooth 4.1 has came.
Yes.
But still Bluetooth speed is not up to the WLN speed.
Right. So the question is Bluetooth. Is it a direct competitor to wireless LAN or not? So the question is, by design, Bluetooth was targeting low range, slightly lower rate than the wireless LAN systems. That was how it was designed. Wireless LAN systems basically said we are starting at 50 megabits per second and are going to move higher. Now, very interesting thing has happened. We'll just touch upon that in the third lecture, but there's a new era of wireless communication that's happening which is non-cellular. That is called the Internet of Things. Basically devices that are connected. You want to have cars connected to the traffic system. You want to have your health monitoring devices connected to the hospital system. All of these systems are going to have to use wireless technologies. So given this scenario, what did the Bluetooth people say? Hey, you know what, if I can increase my data rate, I will capture some of the market that is there for the Internet of Things. Basically smart cities, smart transportation, all of that will require the use of wireless devices. Now wireless LAN people looked at it and said, you know what, why is Bluetooth very attractive? Because it's low power. So what they said was, if I bring a low power version of wireless LAN, then I can compete. So right now they were originally designed for very different, but now both are going to come and compete with the system. So when you say Bluetooth compared to wireless LAN, you have to say which wireless LAN, and there's probably a wireless LAN which is competing with Bluetooth where they both are very, very comparable. So we'll touch upon it, but it's a very good topic to read, because that is happening even as we speak. The cellulars, and by the way, cellular systems 5G 100 megabits per second, but there is a variation of 5G which says I want to go after the Internet of Things speeds, which is low power, low data rate. So basically there is a low power, low data rate mode in cellular which is called narrowband IoT, NB IoT, which is going to compete in the wireless. So you'll have Bluetooth, you'll have Zigbee, and I'll just mention it in the third lecture. You'll have at least 10 other technologies which are competing. Wireless LAN and cellular all want to be in the marketplace where we are talking about low power, low data rate devices, because that's going to be a very big challenge in the future. Good question. Okay, any others?
In the same channel, like in this channel, we have all our cell phones. Suppose we are connected to the same same company, so they do like use the same frequency. Like right now we all use this 4G, so they are like CDMA systems. So they do use the same frequency in the same cell.
Okay, but the 4G actually is using a OFDM technology, but let me answer your question. Yeah, so one of the most important elements in a cellular system, so that user A, user B, two people who are in the same geographical location don't interfere with each other, is that they must be orthogonal in some dimension. Orthogonal in time means that you transmit one time, he transmits other time. So basically you're orthogonal in time. Or orthogonal in frequency. You use F1, you use F2, orthogonal in frequency. Or orthogonal in code. You use code C1, you use code C2, which are orthogonal to each other. You must have orthogonality. The minute you lose orthogonality, you start interfering with each other. So that is the essence of cellular system design. So even though, let's say all the people in this room are connected to the same operator, the operator will design their system to ensure that all of you are orthogonal in some dimension, frequency or time or code.
As long as I maintain the orthogonality of the code, I can like use the same frequency for as many users as I want.
Okay, orthogonality has got dimensions. At some point you will run out of dimensions of orthogonality. So, when you run out of dimensions of orthogonality, we go into something called quasi-orthogonality, where we can maintain something that looks like orthogonality, but it is not perfect orthogonality, and then eventually you run out of quasi-orthogonality also, and then you start interfering. So I think the challenge is, how do you extend the capacity using notions of orthogonality and quasi-orthogonality? Otherwise, we'll see you tomorrow at 11 o'clock. Thank you.